Hello, and welcome to the technical rundown of Spare My Air, a big data case study on Internet of Things. I am your host, Asta Frascati Robinson. In 2016, the American Lung Association reported every county in Connecticut as being at risk for high ozone levels. As a Connecticut resident, I want to understand, is the air quality in Hartford significantly worse than other state capitals? How safe is the air I breathe in Hartford? How does my air quality in Hartford compare to air quality in capital cities nationwide? And how does weather affect air quality? AQI is an index for reporting air quality. The greater the number, the greater the pollution. The EPA monitors AQI for measures that are defined in the Clean Air Act, including fine particle, coarse particle, nitrogen dioxide, ozone, sulfur dioxide, and carbon monoxide. Any AQI value that is under 50 is considered good. Any AQI value over 50 is scaled to moderate, unhealthy for sensitive groups, unhealthy, very unhealthy, or hazardous. To look at a city's air quality level, we are looking for all of the AQIs to be below 50. And we are concerned with any AQIs that are above 50. This April, the EPA installed a Village Green Station at the Connecticut Science Center. A Village Green Station is an Internet of Things technology. It uses various sensors and connects to the Internet to provide real-time data on weather and air quality. This data is tracked at AirNow, a government website that tracks how clean or polluted air is across the country. As the cost of Internet of Things technology falls, the sensors for Internet of Things become readily available to the general public. These types of Village Green Stations could even be built inside your home using Arduinos or using Intel Edisons. The datasets used for this project were state capitals from Wikipedia, weather monitoring station call signs, which were manually found via Wunderground, bounding box coordinates for state capitals, which are provided through the Yahoo GeoPlanet API. There is a key required to access this API. Air quality data via the AirNow API, again, a key is required, and weather data from Wunderground. In total, 41 capital cities had air quality data available for all of April 2016. So hourly air quality and weather data was captured for all 41 available cities for 4/1/2016 to 4/30/2016. All of the data can be found in the file final.csv, so you do not need to rerun the queries to these APIs. The big data technologies used for this project are InfluxDB, which is a NoSQL open source database that is specially optimized for Internet of Things time series data. InfluxDB uses a timestamp as a key and allows a user to define any metadata to associate with that key. Chronograph is an open source real-time visualization tool that connects to InfluxDB. It allows for data exploration and quick creation of visualizations. Both technologies are in beta, and their general availability release is scheduled for summer of 2016. A key benefit of both of these technologies is that they're purpose-built to scale for Internet of Things data. When you imagine one data point being collected from a sensor every second and being sent up to the cloud, this is over 86,000 data points in one day. Internet of Things technologies need to be built to be scalable. Both InfluxDB and Chronograph were incredibly simple to set up, and I was up and running with visualizations very quickly. They are two pieces of a suite that also include a real-time ingestion tool and an alerting tool. Some drawbacks of these technologies is that they are still in beta, so there would be supportability concerns for a production application. In addition, Chronograph is limited to line graphs at this time. There were many times I wanted to create a bar chart or a scatter plot or a box plot, and they were not possible using Chronograph. Future releases plan to resolve this limitation. In addition, Chronograph is missing options for customizing the chart colors, labels, and other customizations typically found in visualization tools. Adding these capabilities would make Chronograph more flexible. To install InfluxDB, we open a terminal window. From the terminal, we type brew install InfluxDB. In my case, I already have it installed, so it'll come back telling me already installed. On your window, it'll go through steps to actually perform the installation. To start InfluxDB, you type influxed. Then you will see a number of parameters run down the window. This indicates that you were able to successfully start the InfluxDB. Next, you can try opening the web console for InfluxDB. That's hosted at localhost 8083. So we will type in localhost 8083 and we'll be presented with the InfluxDB console. InfluxDB is queryable using a SQL-like language called InfluxQL. There's a query reference available on GitHub. InfluxDB can also be accessed via an IPython notebook, which is how we'll load the data. To install Chronograph, open another terminal window. In that window, type brew install homebrew/binary/chronograph. Again, I already have it installed, so it'll come back with this message, but on your window, it'll say installing and then complete. To start Chronograph, type Chronograph. Chronograph also has a web console, so this time we'll launch another browser window and we'll go to localhost 10,000. This is the console where all visualizations can be created in Chronograph. Before we can create a visualization, we need to load our data into InfluxDB. We want to load our IPython notebook final.ipynb and scroll down to the data storage step. In the data storage steps, we want to run the first, second, third, and then fourth steps. The first step will load the final CSV file. The second step will connect to our InfluxDB. The third will create the database AQI, which stands for Air Quality Index. And the last step will load all of our data to InfluxDB. The data is loaded using a JSON structure that defines each measurement and all of the tags that the measurements have. A measurement is, for instance, fine particle, or ozone, or coarse particle. Then each of the measures are tagged with a time and the value of the measure. In all, the data load step could take up to half an hour to complete. Take a break and then come back. Once the data load has finished, go back to the InfluxDB web console at localhost 8083. In the console, we want to choose the new database we created, AQI. And then we want to type in the query show measurements and click enter. Here we can see that all of our measures have loaded to the database. Our load was successful. We are now ready to create a visualization, so we return to the Chronograph console. In Chronograph, we click the plus sign to create a new visualization, and we're going to call our visualization New Visualization. And then we'll click Save. The first thing we want to do in Chronograph is choose our time frame. All of the data we loaded was for April 1st through April 30th, so we're going to choose custom time frame. And then we choose April 1st to April 30th, and we actually want to start at midnight and finish at midnight. And click apply. We choose the measures for our visualization. For this visualization, we're going to measure the fine particles. So we click the drop down and choose AQI fine particles. We're going to extract by the min value for this visualization. So we click min. And then this is showing the min value for fine particles across every hour for every day collected in April. We can click Builder to hide the query row. To simplify creating the rest of the visualization, we can click the Duplicate Query button. After duplicating, if we expand the builder, we can change the value from min to max. Now we've shown the min value and the max value for fine particles. We'll copy the query again, and instead of max, we will change it to mean. We'll copy the query again, and this time we're going to manually edit the query. We're going to add a plus sign and then STDDEV, which stands for standard deviation, and then we'll type value. So we're looking at the mean value plus 1 standard deviation away from that value, and then we'll press enter to execute that query. We will copy that query, and instead of adding 1 standard deviation to the mean, we'll subtract 1 standard deviation away from the mean and click enter again. There's one more query we want to add to this visualization, and this is to look at a particular state. In our case, it's Connecticut, but this query could be changed to look at any state of interest. We choose to filter by the value for AQI fine particles one more time, and then we choose the state of Connecticut. Now we are able to see the min, max, mean, 1 standard deviation away from the mean in both directions, as well as the state of Connecticut's fine particle reading for all of April. We can see that on April 22nd, Connecticut reaches the peak of fine particle AQI. This means at this time, on this day, Connecticut had the worst AQI across the nation. However, this is not of concern because this value is only a little bit above the normal range of 50. And second, there's another state that has a far greater max up into the 150 plus range, which is much more concerning. If we want to see more detail on the peak of interest, we can click and drag to zoom in on the graph. Here we can clearly see again that on this day, at this particular time, Connecticut had the worst AQI for this value. The same process can be followed to create additional visualizations to explore all of the air quality indices. The IPython notebook can also be used to create visualizations which were not possible within Chronograph. In conclusion, in April 2016, Hartford measured fine particle AQI, coarse particle AQI, and nitrogen dioxide AQI. This represents 3 of the 6 possible AQIs that are measured nationwide. All hourly coarse particle AQI and nitrogen dioxide AQI readings were normal, which is a measurement below 50. There were 28 hourly fine particle AQI readings above normal that were classified as a moderate health concern, and Connecticut ranks 6 of the 24 states with readings above normal. The fine particle AQI readings spiked on April 22nd, which coincidentally was Earth Day. Yet I wasn't able to find any additional information of what may have been going on in Hartford that day that contributed to the spike. For all of the measures captured, there was not significant air quality health risk in Hartford in April of 2016. To improve the analysis, Hartford should measure and provide data for all of the AQIs, which should soon be possible with the installation of the Village Green station. Overall, through completion of this project, we can see that through all of April 2016, there was not a significant air quality risk in Hartford, Connecticut.